And yeah, so I forgot to say, this week's lecture is on clustering, which is heavily different than the sequence that the book has given you. Because I don't like the sequence of the book in general. It's just a personal preference. And I don't know, I think, so the reason why I decided to start with clustering is that I believe that clustering is one of the most, clustering in general as a concept is one of the most intuitive, if not the most intuitive idea that people have when they think about patterns in data, right? So it's because patterns themselves, like when you just say, oh, I'm looking for patterns in my data, that's very abstract. We have an understanding, like a informal understanding, that a pattern in a data set, it's something that is not random, right? Or that is very close, very far away from being random. Because of course, maybe a real world data set is never completely random, but some things are close to random, or at least they look random. And usually when we think about a pattern, we're thinking about something that's not random, right? So detecting patterns in a way could be seen informally as detection of things in a data set that are not random. And the fact that they're not random, or they're very far away from being random, they kind of bring you some insights about that data set, because they bring you some idea about actually the phenomenon that's underlying that data set, right? Because when you think about data sets, they're always, you can always think that they're a sample of something in real life, right? You extracted them from that data set from real life somehow, and for some reason. And every data set is a different thing extracted from a different event. But you can always think that the data set is just a sample, a small sample of something much bigger, right? So in that you can be thinking about statistics. Probably you've studied statistics before, and you've seen the concepts of population and sample. So you take a sample from the population in order to try to understand the population through the sample, right? Because the population is, let's say, unreachable, while the sample is reachable. So the sample in this case is your data set. And when you look for non-random things in your data set, which we call patterns in general, then you're looking for, you're trying to understand the phenomenon that's behind that data set, from where the data set came from, right? And something being non-random means that you can actually understand it, and you can actually take some insights from that. Because if it's something's just, if there's just some random behavior in your data set, then basically it's very hard to just conclude anything, right? And I think that clustering, from my experience, whenever I talk about patterns, my research is on visualization. So whenever we talk about using visualization to understand a data set and detect patterns from a data set, most of the time people think about clustering. Oh, I want to find clusters in the data set, because it's just kind of, I don't know why, I can't explain that, but I think there's a natural thing in the mind that says, well, if points are grouped, then that kind of like, that means something. There's some kind of an underlying pattern there that makes these points become grouped, while these other points are grouped elsewhere, and so on. So then I decided, you know what, I think clustering would be a great first lecture, because then it's not something that's far-fetched. It's something that's close to everyone, and then we can take our first step into this idea of just extracting patterns from data. Okay, that's my reasoning, and I hope that, and also a little bit about what we do in the course. Now, just very quickly, you probably have studied machine learning before. Most people do nowadays. Like when you're 5 years old or something, everyone is studying machine learning all the time, because it's such a big deal nowadays. And that's perfectly fine. But most of the time, I'd say when you study machine learning, you're studying supervised learning, right? So you have like labels or some kind of that of stuff that you want to predict. You want to teach your algorithm to relate to some features that you have with some kind of a response, some kind of a label or some kind of an output variable that you have, and you want to kind of connect them both, right? And we talked about that in the introduction already. But in this case, when I talk about okay, so that was a yeah. In our case, when you talk about clustering, that's not really the case. We don't have this thing here. All we have is this thing here, right? So we talked about this already in the introduction, but just as a recap, we're talking about unsupervised learning here, okay? There will be cases when we will use labels in order to evaluate or assess our clustering in order to try to determine if the clustering actually makes sense. But that's like an external evaluation of the cluster, okay? It will never be used to actually do the clustering. So basically, the important part here is to remember that what we have as input is this thing, right? We're not talking about networks and other things right now because they will come later in the course, and then we will come back to this idea of clustering networks, which is actually like usually more well known as like detecting communities in a network. But which is it's a concept that's very related to clustering, but not exactly the same. So for now, as it is right now, we're dealing with structured data sets like this, okay? And if your data set does not look structured like this, then you need to take another step in order to make sure that it is structured like this, okay? So let's say you're working with text, for example. Text by itself is not structured, it's just text. So then there are lots of different ways that you can actually turn a text into a structured data set like this, all right? And I'm not going to deal with that right now. So let's just assume that what you have is this thing here. It's every row is a data point and every column is a feature. And then we're going to discover patterns, groups, subspaces, manifolds, and so on and so forth. All of these are possible patterns that you can extract from data, and they are a little bit different. But in this case, of course, we're going to be talking about groups in this lecture specifically. Unsupervised learning is in general very challenging because it's subjective. So there is usually not like a simple, straightforward goal. You could run different algorithms and they will tell you different things about your data set, especially when you're talking about multidimensional data sets like this one, for example, that has P dimensions or features. So whenever I talk about dimensions, just assume that I'm talking about features, okay? And it's very hard to assess the results because there's no cross-validation or no true answer to check. Like you can't say that one is right and the other is wrong unless only if you're talking about some very, very simple data sets, right? And this works for every technique that we're gonna see in this course. There's never one final true solution, or if there is, then that's because the data set's so simple that's obvious, right? And then it becomes obvious, and then you say, yeah, obviously this is right, and obviously this is wrong. Like with the data sets that you have in your weekly assignment, in those cases, you have some very clear solutions. That's why I added them as examples, because or else that wouldn't make much sense. So they have clear solutions. Like, for example, you have two moons that are like this, one is inside the other, and we have a very clear solution for that. We want the moons to be separated into two different clusters. So in these cases, yeah. But most of the time for real world data sets, that's not how it works, okay? And there's no very easy way to just cross-validate and stuff like that. So usually it's used for exploratory data analysis. You're exploring your data, trying to understand what it is and what's in it, right? It's a little bit different than what you do usually in supervised machine learning. And then basically unsupervised learning is clustering and dimensionality reduction, which are the first couple of subjects that we're going to talk about together with distance measures. And then later we will move on to some other stuff. But basically we're kind of gonna start from this as an entry point into the data mining world. okay? And now clustering, finally. So please make sure that you ask questions or raise your hands if you have anything to add to the discussion. Now, clustering, techniques for finding subgroups in a data set, right? Each element of a data set usually belongs to one and only one cluster. Usually, there are techniques that will give you like probabilities as results. They are not part of the, let's say, traditional or the most common clustering techniques, but they exist. But most of the time, it's just like, okay, this point is in this cluster, this point is in that cluster, and that's it, right? Whether that's good or not, who knows? Elements in a cluster should be similar to other elements in the same cluster and different than elements of other clusters. This is kind of like one of the basic tenets of clustering, right? If a point is in a cluster, then you assume that it's more similar to the elements in that cluster than it is to the elements in other clusters. And I mean, it doesn't necessarily mean that you have different, like you have, thanks, Chen, for distracting me. And that does not mean that they are absolutely identical or super similar to those who are in the same cluster, and super absolutely different than the elements on other clusters, right? It's just that you expect them. If you take a clustering result, someone gives you a clustering result and said, hey, this is a clustering, then you expect that those points that are in the same cluster are more similar to each other than they are to elements that are not in that cluster, right? It's an assumption. Whether it's correct or not, it's hard to say for sure, but you assume that. Now, this is the classical example of The Simpsons. Probably you've seen this before, but I think it's a nice example. So, like, for example, you have these guys who are Simpsons characters, and then you say, okay, I want to cluster them into two groups. Does it make sense to cluster them into Simpsons and not Simpsons? So then you have the Simpsons family here and the ones that are not part of the Simpsons family. Well, that's one clustering. That makes sense, right? But it would also make sense, for example, to cluster them into male and female. Yeah, well, actually female and male in this case. Yeah, that would make perfect sense. Like that, which one is the right one? It does. I guess it depends on the scenario, the context that you're using, the reasons why you're doing this, we don't know. But the important part is to remember that there is no final solution, especially when you have multidimensional data sets. So multidimensional data sets, they vary, they have variance in many different ways, many different axes, let's say. So it's possible that you can cluster them in many different ways, and all of these clusters could be reasonable. The definition of what it means to be similar or different is not, there's also not one single way to determine that, right? There is a very common way, which is the Euclidean distance, and it's perfectly fine to use that in the beginning when you're dealing with structured data sets like this. But we will see later, because we will also have a little bit of content focused only on distance measures. So you will see that Euclidean distance is not always the final solution or even the best one, okay? So you can calculate similarity or difference between two things in different ways that would make more sense in different cases, especially when you're dealing with non-Euclidean data. So sometimes, like a network, which is a common example, right? Or text, in case your text is not structured, you could have some other similarity calculation between text that does not necessarily have to structure a text as a vector, as you need when you do Euclidean distance, right? But for us right now, we're gonna consider that, you know, this data set is an Euclidean data set, so that means it comes from an Euclidean space. Although, like I said here, the data sets are a collection of points that come from a certain space, where a certain distance is defined. It doesn't have to be Euclidean, but Euclidean is the most common example, so we're gonna go with that for now, right? This is, for example, a data set from a p-dimensional Euclidean space, right? So because we have p dimensions here, so we sampled this from p-dimensional Euclidean space. And I have n points with p dimensions each. And this would be the definition of the Euclidean distance in p dimensions. But remember that Euclidean distance can be calculated in any dimension, arbitrary dimension. So no matter no matter your, let's say, the length of your vectors, no matter how many dimensions you have, the Euclidean distance can still be computed normally. So that's why I guess it's one of the most common ones also, because it's so easy. You don't even have to change it for different dimensionalities, right? But you can have, like, for example, yeah, so however you will work with other non-Euclidean spaces, like for example, in a network, you can have shortest path or some other measures, and that would still work. In a text, you have added distances, for example, for strings and things like that. So as long as you have points and you can compute some similarity or some distance between them, it's okay most of the time, all right? We will just go on with Euclidean, but we will come back to this later when we talk about networks and text and so on, and also distance measures. So one intuitive example for clustering here, this is a two-dimensional example. So P here equals 2 in like this p-dimensional data set. And this is a bunch of dogs, and basically they measured two things about the dogs. This comes from the course literature. So the weight is in the x-axis and the height is in the y-axis. And then they just plotted this, right? And immediately you can see, well, of course, when you plot this for the first time, right now it's obvious because the points have different colors, and also they have labels. So if we suppose that there were no labels and there were no colors, that everything was white like this, you could still very easily see that there are 3 clusters here, right? Because you can still see that they are grouped into 3 groups. And that's the kind of thing that I was talking about before when I was talking about patterns. What is a pattern? Well, a pattern is something that strays away from being random. And in this case, if there was no connection between height and weight, then you would see basically just a blob of points, because then basically like weight and height are completely independent from each other. And you would see just a blob of points, and you wouldn't really be able to extract any kind of interesting pattern from it. But this is not random, so the less random it is, the better, right? And in this case, this is very, very far away from random, because you have one group more or less here with a low height and low weight. Then you have another group here that has low height but high weight, and then you have another group here with high weight and high height. So then you could, just by looking at it, you could detect this. And then if you look at the actual data set and you validate it, you would see, yeah, actually these are the Chihuahuas, these are the Dachshunds, and these are the Beagles. So because they have so different characteristics, right? But of course, for high dimension or non-Euclidean spaces, this is much more challenging, because first of all, you cannot visualize a high dimensional space like this. And you can visualize non-Euclidean spaces if you use some kind of specific visualization technique, but it's up to you, and there is no one final way to visualize a non-Euclidean space. So you may or may not see the patterns depending on which visualization you choose. And of course, so this is of course just a very, very simple example of two-dimensional data. Well, let's just go. Yeah, so basically what I wanted to say here is, coming back to the slide, is multiple dimensions of categorical data means that there is no single final solution. So you already discussed this, but basically it's that since these points here, they have multiple dimensions of categorical data, like I'm a Simpson or I'm not a Simpson, or I'm a man or I'm a woman, or I don't know, I'm a child or an adult or something like that. All these things, they can be used to cluster your data. But most of the time what will happen is that we will cluster on multiple dimensions at the same time, not just one, right? But it's just a simple example. But just remember that in real examples and real applications, you don't cluster per dimension. You cluster usually by combining all dimensions at once, or at least most of them. And now we start with the actual clustering techniques. And we will start with k-means. So the first 2 techniques that we're going to see are k-means and the hierarchical agglomerative clustering. I will go quickly through them because they are very, very basic, and the most, and I think it's more interesting to focus on the later, more like recent and more interesting techniques that we have on the second half of the lecture. So I will just go through k-means and hierarchical agglomerative algorithms just so you guys get like an idea of the basics of clustering, and I guess also that you have already seen this somewhere else because these are so common. But anyway, it's important that we establish the baseline here. Okay, so k-means partition the elements into a predefined number of clusters. So most techniques will ask you to predefine the number of clusters, although not all of them do, but most will, and k-means does. And the goal is to minimize the intra-cluster variance, right? So simple examples: 2 clusters, 3 clusters, 4 clusters. So I guess for 2 clusters here it's very obvious. For 3 clusters, maybe. For 4, I guess it just starts to become like, yeah, well, k-means will give you as many clusters as you ask for. So when it comes to 4, yeah, I mean, maybe this is the best clustering possible, but I wouldn't say that's natural, and probably not natural. While these two are, this one's not super natural, this one's kind of natural, I would say, subjective analysis. But the goal is to minimize the intra-cluster variance, okay? So if you know a little bit of statistics, you know the variance is usually defined as the squared error to the mean, right? In a 1D data set, it's the squared error that of all sum of squared errors to the mean of that data set. And in 2D, that kind of works more or less the same. It's just that it's the squared distance, let's say, to the centroid of the point. So if you take the mean point, so to speak, here in the middle, then you take the sum of the squared errors of all the points, and by error, I mean distance, right? In this case, error, it makes sense in 1D. So in 2D, it's more like a distance. So if you take a mean of the cluster, which is like some point over here, for example, that doesn't really exist, but you can compute it by taking the mean of the 2 dimensions, then you have it. And then you take the sum of the squared distances of all points to that mean. That would be like the intra-cluster variance, right? And you're trying to minimize that with k-means. And since we ask for 2 clusters, then and that's why like the number of clusters is fixed, because then you have to say, okay, I want 2 clusters, period. So I need to find 2 clusters such that the intra-cluster variance of these 2 clusters is the minimum possible. This is a definition, like a very, very rough take on the algorithm of the k-means. And disclaimer, you will find different versions of k-means algorithm in different books. That's perfectly fine, because the goal of the optimization is to minimize intercluster variance. But unfortunately, there is no just one final way to do it. Different people will do it a different way, but they will try to arrive at the same final, like, objective conclusion, right? And so we start with random clusters, as is common with optimization procedures in general, right? I mean, not all of them, but most of them will just, let's start with one random solution that I have no idea if it's good or not. And then let's improve it step by step. So with k-means, it's exactly the same. Start with random clusters. So in this case, every element is included in a cluster randomly. And so in a cluster K, so for example, if we have 2, if K equals 2, then we have every point is just randomly assigned to one of 2 clusters. Then you get like a completely messy solution that makes no sense. But it's one initial random solution that we use to start the process. And again, you will see, this is probably one of the points that vary most with implementation. So you will see they go people do all kinds of things here. I don't know which one is better. I wouldn't really go there here to say one is better than the other, because you would need empirical results for that. And I don't think that's the point here. The point is that you start from somewhere. Then you compute the centroid for each cluster. And the centroid is that thing that I talked about. The centroid is the vector formed by the means of each feature of every element in the cluster. So for example, if you have 2D data like we have here, then the centroid is basically the mean of both the x-axis and the y-axis. Then you have like one artificial point that doesn't exist, but you get it. It's somewhere there. I got a question here, but all the algorithms reach the same conclusion, right? Not the same conclusion exactly, because this is not a optimization problem with a global, with, well, it could be, but not all the time. It is like for simple data sets it might be, but not for most cases. It's not an optimization solution that has one global solution. If that was the case, then yeah, every algorithm should at least arrive at the same result. But the truth is that there could be slightly different final results to the algorithms that would be like equivalent, or at least slightly different, but more or less the same. And you can get into different solutions depending on the different starting points. So we will talk about this a little bit in a couple of slides, and then you let me know if you understand, if that is clear to you, or else I can try to explain that again. But this is not a problem that has one final global solution and that's it, right? You can arrive at different local minima, let's say, as it is common with, so Lisa, if it's okay, you can ask the questions on the global group chat so that other.
Sorry, you lost your voice in like.
Just a second. We have too many people talking at the same time now. Let me just answer Lisa. K-means is also a hierarchical algorithm. No, we just specify the number of clusters in advance. I wouldn't say so. When I think about hierarchical algorithms, I think of them as clusters within clusters, right? So like, for example, you have one cluster that includes the whole data set, and then you break that cluster down into two clusters. And then if you want to have three clusters, then you would like break another cluster into one of these two clusters into two more clusters, and so on. K-means does not work like that. So I haven't seen anyone consider K-means as a hierarchical algorithm. I don't want to say no, that never is, because maybe you have seen someone refer to K-means as a hierarchical algorithm, and then I might be interested to see why. But from my understanding of hierarchical algorithms, where clusters are arranged into subclusters and so on, K-means would not fit into that definition. But we're gonna talk about hierarchical algorithms in a few minutes, and then, well, you will be gone, but then you can look at the recording and then come back if you still think that there's a problem, that there's a question there. Sorry, there was someone asking a question. Was you Christian, I think?
You ask the question.
No, I just say that your signal is a little bit unstable.
All right.
I lost when you're speaking. I lost your voice.
All right. Is it better now?
Yep.
Okay. So I will go on, and let me know later again if you think there's some problem. So yeah. So we started with random clusters. We computed the centroid for each of these clusters. And again, the centroid is simply a vector formed by the means of each feature. So it's just like this artificial point that doesn't exist, but you just take the mean of each feature. And then you reassign the clusters of every element in the data set such that each element is in the cluster with the nearest centroid. So you forget about the previous like random clustering that you assigned, and then you reassign every point to the closest centroid, because you get two centroids, right? You have two clusters, and then you get two centroids. Now you just take every point and then reassign them to the cluster with the closest centroid. So you have a new clustering assignment. And then you keep doing that. You keep doing that. You just go back to step 2, and then you take these points, and then you recompute the centroid for them. The centroids will change a little bit, and then you reassign them, and you keep doing that for a while, either for a specific number of iterations or until your cost function goes below some lower limit that you have set. There's no final solution to that. Most people just go on for a few iterations, or until it doesn't change anymore, right? And I forgot to to illustrate the steps here. So this was step 1, where every point was assigned to a random cluster. So we are using 3 clusters here. These are the clusters. the centroids, sorry, that were computed from these random clusters. As you can see, they make absolutely no sense. Then these are the points reassigned to the new centroids. So every point was simply assigned to the closest centroid. This is the new centroids that are computed after reassigning the clusters. So you can see that now they actually moved quite a lot. And these are the final results. So maybe you don't see it, but it's a little bit different than the previous one. So if you run this for a few iterations, you will see that they will change a little bit, but not much actually. Usually it's after a couple of steps, they're quite stable already. It just doesn't change that much. But yeah, this is an optimization process, right? So it's iterative, starts from a random solution and improves that solution at every step, which is basically just a common framework for optimization, at least when you talk about gradient descent. In this case, it's not gradient descent, but it's just a general optimization process. This is a math formulation of this thing. I will skip that for now because we have other stuff to talk about, but you can take a look later and let me know what you think. So finding the optimal partition of a data set into k clusters according to the specified goal would involve around k to the 9 operations. That's not feasible. That's why, and I think now I'm again coming back to the Christian's question, which is Christian Leone. Not I don't know why we have two different people with very similar names, but anyway. So, and I think Christian Lyon is actually Shen, if I'm not mistaken. So correct me if I'm wrong. But Christian Leone's question was whether all algorithms reach the same conclusion, and the answer is in general no, because like I said, because like it's written here, what happens is that if you would do that, then if you would find the actual final solution, you would have to run all k to the 9th power operations, and that's absolutely not feasible. So that's why we need this faster optimization process that may or may not reach the actual final solution, and it usually just falls into some local minima that is not perfect but very good. And each different procedures might end up in different local minima, but they should be equivalent or at least very similar. Okay. Yeah. So, but yeah, the final solution is based on the initial configuration. Okay. So that's why we use random, because since we don't know what is the best possible initial configuration, we cannot know that, then we must use some kind of a random initialization, or at least some people have tested different things. I will not go into that. Maybe sometimes something else is better, but if you have no idea, then random is for sure your friend. And usually you don't have any idea. This is the same exact algorithm of k-means executed with 6 different random initializations. Exactly the same, but with you run it 6 times with 6 different random initializations. And then you can see that sometimes it kind of looks bad like this or like this, but most of the time it looks good. Actually almost identical, if not identical. Just the colors that have changed, but the colors don't matter, right? So the best solution was found 4 times here. So if you run it like 10 times and then you see that there is a certain solution that is more frequent and with less sum of squared errors, which is also known as internal cluster variance, then you can select that. So if you're not sure that, if you don't want to run just k-means once and then say, yeah, that's it, because you're not sure, then run it a few times and then take the one that gives you the lowest cost, for example. And that's more or less like the best we can do. There's a simulation of k-means here, and I will just leave it for you guys to take a look later, because it's really nice and it shows you how k-means works and everything. And I wish I could just have a million hours to show you everything, but I don't. So since I want to talk about some other stuff that's more interesting, then I will leave this as an example for you guys to check later at home. But I really recommend clicking this link and then just playing it around with it for 5 minutes, because it's really cool. Also, the random initialization is not the main factor, right? So the number of clusters is probably the most important parameter, because that's what really affects the results, right? If you say, okay, I want 2 clusters, or I want 3 clusters, or I want 4 clusters, then that changes everything. Unless your data set is super obvious and super clear, then you don't know exactly how many clusters you have, right? Usually. So one way to choose K is with the so-called elbow method. What's the elbow method? Well, you run your cluster, your algorithm k-means for a few different Ks. So in this case, for example, 1 to 10. So I run it 10 times. Not me, I mean, this is from the book. Well, actually not even from the book, from this example here that's here. So it's ran like 10 times. And then you take the sum of the squared errors finally. After the algorithm is done, you just take the final sum of squared errors. That's like the final state of the system, or the final value of this cost function that you're optimizing. And then you plot it into a plot like this, with the number of clusters here and the error here. And then, as you can see, with one cluster, that's a lot of error, but the one cluster doesn't mean anything, right? So with 2 clusters, it goes down quite sharply. So the error goes down, that's good. And then from 2 to 3, the error still goes down quite sharply. But then at some point, it starts to go down more slowly. And make no mistake, the sum of squared errors will always go down. And it will keep going down until you have k equals n. So every point is in its own cluster, and that's the minimum. But that's not what you want, right? Because, I mean, that makes no sense. So it's not about finding the minimal value here, because the minimal value will be when k is equal to n. It's about finding the place here where the tendency slows down. The tendency of getting less and less error slows down. So as you can see, it's probably around here on 3, because it goes down sharply, then it goes down sharply, and then it goes down a lot that sharply anymore, and even less about after this point here. And this is the data set. It's a 1D data set. So I mean, if you look at it, you can see that there's a dense part here, there's a dense group here, and there's a dense group here. So I guess 3 clusters kind of make sense for this data set. So I guess it would make sense to then consider that the 3 here is the elbow of the graph. And in the case of data set B, in this case, it's not like super clear. You don't have a super clear partition of points here, although you might say that, yeah, there's kind of like a dense part here and a dense part here. So 2 might make sense, right? But 3 could be pushing. So you can see that from 1 to 2, still you have a very sharp descent, and then it slows down this from 2 to 3, and then it keeps slowing down. So I'd say that maybe the elbow here is probably this one here. I guess this one is stronger than this one. So I would say that the elbow would be on 2, and then you would get probably a big cluster here and a small cluster here, for example. Another question to Christian. Since we have to run this algorithm a bunch of times, would it make sense to implement an early stopping on the movement of the cluster means? By early stopping, I believe you say, like, if the cluster means or the cluster centroids are not moving that much, they're kind of stable, then you just stop, right? Is that what you mean? Well, if that's what you mean, then yeah, absolutely. I think it's a good idea. Just, of course, these things are not final, right? There is no like final way to say how much is a little moving, right? Because you say, well, if the cluster centroids are moving just a little, then stop. So you could have a parameter for that. Absolutely. That makes a lot of sense, yeah. So you have a parameter like, okay, if the cluster centroids move less than a certain number that I decided, then just stop. And yeah, it would definitely make sense. I can't tell you for sure that mathematically that would be correct, because I can say that, you know, the clusters are not going to start moving again later. It could happen, like they move a little bit and then they start moving again very much. Who knows? Could happen. But I would say that probably yes, probably is a good idea. And that's how data mining works anyway. You never know for sure. I mean, some people do formal math proofs, but we won't. So in general, they are heuristics, and yours is just as good as any other. Okay, so that's it for k-means, guys. Very quick introduction. Now we're going to talk about very quickly about hierarchical clustering, which was what Lisa was commenting on. That k-means was k-means also hierarchical clustering, not in the way that I understand hierarchical clustering, but again, like I said, maybe someone that has defined k-means as a hierarchical clustering method with some other definition that I'm not aware of, which could happen. But as far as I understand hierarchical clustering, no. Because what happens with hierarchical clustering is that you don't have a predefined K. So you don't have to have a predefined K, because you actually cluster your data into every possible clustering from 1 to K. So every possible clustering, from having just one cluster where all the data set is in that cluster, and on the other end of the spectrum where every point is in its own cluster, so you have as many clusters as data points. Every possible solution from these two ends of the spectrum is considered. And then it's up to you to say which one you want. So first you generate all of them, and then you say, and then you look at them, like for example, looking at a dendrogram like this, and then you decide, well, I think it makes sense for me to break it down into 3 clusters, or into 4 clusters, into 5 clusters, whatever, depending on how you visualize the actual solution. And the reason why it's called hierarchical, and again, that's why I said that I don't think k-means is hierarchical, is that every cluster is inside other cluster, right? So for example, let's say you have, again, start from the simplest one. You have every point in one cluster. So there's no pattern there. There are no patterns there, right? It's just one big cluster. And then you say, okay, next step, 2 clusters. Then you take this big cluster and you break it down into 2 clusters. And then when you take the next step, the third step, which is like, okay, now I want 3 clusters. Then what you do is that one of these 2 clusters will be broken down into 2. And then you get 3 clusters. But you see how these 2 smaller clusters, they are contained actually into, they're contained in this previous big cluster that was there before. So that's why it's hierarchical, because each cluster is breaking down into smaller clusters and so on. And that's what you see in this tree here. And in that sense, k-means is not hierarchical, because if you run k-means for 2 clusters, then you get a result. If you run it for 3 clusters, these 3 clusters that you're seeing, they are not necessarily hierarchically related to the solution with 2. So not necessarily 2 of these clusters that you see on the new configuration are actually contained inside one of the previous clusters that you got. That might happen, but that's not necessarily will happen. You may just find 3 completely different clusters that completely mix up the 2 previous clusters. So that's not hierarchical, as I understand this. However, that's one important point here. This thing that I described is not the kind of hierarchical clustering that we're going to see now, because I was talking about top to bottom algorithm, where you take one cluster, break it down into 2, and then you take another cluster, break it down into 2, and so on and so forth. What we're going to do is actually the opposite. We're going to start from the other end of the spectrum, where all clusters are in their own, or all points are in their own cluster, so you have as many clusters as points, and then you're going to start merging points 2 by 2, or merging clusters, let's say 2 by 2, and then slowly you walk up the hierarchy until you have 1 cluster at the end. But we're going to talk about that. So very quickly, algorithm, bottom up, or agglomerative algorithm, as we say. So again, bottom up, okay? That's not top bottom, as what I was talking about in the previous slide. Both of them exist. Both of them have many different available algorithms. They are, I guess, both reasonable, But at this point here, we're just going to talk about bottom up, according to the course literature, but not the. Actually, you have this in the course literature also, but this is more according to the actual the other book, because I think it's a little bit better. So you start with each element in its own cluster. Again, we have here a number of clusters, 9, because we have 9 points. So there are 9 clusters, okay? In an empty dendrogram, because we don't have anything. Then we merge the 2 most similar clusters into a new one. And when I say 2 most similar clusters, please understand that at the beginning, that means the 2 most similar points, because every point is in its own cluster. But we have to already start thinking in an abstract way about clusters, because this is how the algorithm works. And since we're going to repeat this many times, then we need to think about clusters and not points. So after step 1, and since every point is in its own cluster, there are no points anymore. All we have is clusters now. So we forget about points and we only think about clusters, okay? So we merge the 2 most similar clusters into a new one and add them to the dendrogram at the similarity height. So for example, these 2 guys have a similarity of 0. Something below 0.5 here, so 0.4 or something like this. So then you merge them and you put them here, because this is where more or less the similarity is. Then you repeat step 2 until there's only a single cluster. Actually, it's the most simple algorithm you could ever imagine. And you can see that if you go back to step 2 here, you say merge the 2 most similar clusters again. So again, find the 2 most similar clusters in the data set, merge them, and put again the similarity here, like wherever it is in the height here of the dendrogram. Put them here, repeat step 2. Now, in this step, this is interesting, because now we didn't merge 2 points anymore. We merged 2 actual clusters. Even though we were doing that before, but still. And this generates one interesting question. How do I compute similarity between clusters? Because I mean, when each point is in one cluster, then that's okay, because they're just points. So I just compute the distance between them. But when you have actual clusters with more than 1 point, then then there's something ambiguous there, right? What does it mean to calculate the distance between clusters, right? And that's where the linkage comes in. Now, I have a question from Christian Leone. Do we check similarity couple by couple? Yeah, if I understand what you mean, is if you should check all the pairs of clusters in your data set in order to find the best one or the smallest one, right? If that is the question, then yes, you do that. At every step, you have to check all of them. And that's quite slow, actually. Yeah, for each point against all of the others, yes. Although, of course, it gets a little bit faster as you go, because then you have less clusters, and you begin with a lot of clusters, but slowly you get less and less. And also, in many ways, you can reuse the distances that you already know, right? But yeah, you do that. So that's pretty slow, actually. But what if you have 10,000 points? You don't use the clustering. I would say that using hierarchical clustering for 10,000 points would be quite problematic. But as it is with most other algorithms, there are always new optimized versions, right? Actually, if you read the mining of massive data sets, so I will call it MMDS book, the chapter on this, or the section on this, there they describe one possible optimization using a priority queue. A priority queue. Actually, I'm going to talk about this in a few slides, and then you let me know if it's enough or if you need more. Okay, but there are optimizations, yes. Although it's still it doesn't become like super fast all of a sudden, but you can optimize it a little bit. So so the similarity between 2 clusters, again, it's a little bit ambiguous, right? You have to think about like what does it mean, because it could mean a lot of stuff. And the truth is that there is no final solution, again, as always. So you could choose between a few options, and each one of them will have a different impact on the solution, right? So for example, average and this is what we call the linkage, and this is a parameter of the technique. You have to set it beforehand and before you run the algorithm, and we call it linkage. So the average linkage, for example, is the mean distance between all points from A and B. This is kind of slow because then you have to come here and take all the pairs of points between the two clusters, consider all of them, and then take the average distance, and that would be like the distance between the clusters, right? So, but that's a bit of a problem here, I guess, because then you have to really compute all of them. Although maybe to a certain extent you have to do it with all the others too, but there are ways to optimize it. So single linkage is the smallest distance between points from A and B. I would say that probably single linkage is the most used. Maybe it's hard to say, but I would say I have a hunch that single is the most common. So the smallest distance between 2 points from A and B. So for example, in this case, it would be the distance between 8 and 5, because 8 and 5 is smallest than 8 to 7. So we consider that the distance between 8 and 5 is the cluster distance. Okay. Then complete is the largest distance between points from A and B. So it's a little bit like the worst case, right? So in this case, it would be the distance between 8 to 7, because that's the largest distance between any point from this cluster to any point from, well, not this cluster because actually, well, yeah, this cluster because 8 is in its own cluster. So this cluster of 8 against this cluster of 7 and 5. So that would be 8 to 7. And then there's centroid linkage, which is the distance between the cluster's centroids. And this is different than the mean distance. Okay, guys, it's one thing to take all the distances and then compute the average one between all pairs. And it's another thing to first find the centroid of the cluster and then compute the distance between the two centroids. And that's much faster actually, because in this case, you're not considering like multiple possible pairwise distances. You're just computing two artificial points and then computing the distance between them. So that's much faster. But there are also problems with that, as we will see soon. And it also only works for Euclidean spaces, right? So you cannot, this doesn't work if you can't find centroids, because you can only find centroids if you're talking about Euclidean spaces, because then you have vectors. But if you have a network or text or something like that, then you might not. There are ways to adapt this, but centroid itself as it is doesn't exist in necessarily, or not that it doesn't exist, but we don't know how to compute it. So yeah, I think single is the safest one to use usually. And this is the final result of that example that we saw. And it's very interesting to see that, like for example, well, and this is the full dendrogram. And this is, I don't want to be 100% here, but I think this used single linkage. I'm pretty sure that it was single linkage, this one. Then you would have to look in the book, but I think so. But it's very interesting to notice that, for example, 2 and 1, if you completely remove the clustering partition here, they are very close to each other, much closer than 2 is to 8, for example, or to even less to 9, right? But they are separated. So this is the kind of stuff that happens with clustering because of the algorithm, right? And if you run the same algorithm with a different linkage, like complete linkage or even mean, then you will get different results that may or may not make more sense to you. And unfortunately, there's no like final way to decide it. But one thing that we do try to maintain is, yeah, this is what I wanted to show. Yeah, the one thing that we usually try to maintain is to have a kind of balanced dendrogram, right? So in this case, for example, the complete linkage to me looks a little bit more balanced than this one or this one. So this one kind of looks a little bit weird because there's a lot of like single points clusters here, which is usually not something that you want to see. And this one is not bad, I guess. But to me, it seems like complete linkage is the most, let's say, balanced one. So usually we try to keep the dendrogram balanced. So that's one way of choosing the linkage, for example. But what I wanted to say here is that when you use a dendrogram, it's important to remember that if you look at the dendrogram, you shouldn't compute distances in this dendrogram. Like, for example, 9 and 2. 9 and 2 in this dendrogram here are very close to each other, but that means nothing. So forget about it, because you know, it's they are in the same cluster, but they're not actually, you know. So it's you know, it's the dendrogram is just a dendrogram. It just means that things are you know, in the same cluster. And yeah, and you make a horizontal cut like this, and then you cut here, for example, into 2 clusters, and then you have the red one and the green one, for example. And then if you wanted 3, then you would cut down here, and then you would have actual these 2 clusters plus 9 as a cluster in itself, because it's kind of like an outlier. So it actually makes a little sense to have that. Yeah, so the resulting dendrogram changes a lot, and usually you want to have a balanced dendrogram, and average and complete linkage, you tend to generate more balanced dendrograms. Centroid linkage is a problem. Even though it's the fastest one, it has this problem where it generates fusions below the centroid's position. So the dendrogram goes back down because of how the centroids work. Sometimes when you compute a new pair of centroids after you've clustered already a few points, then actually the centroids get even closer to each other than they were before, which is not the case with the other dendrograms, because with the other linkages, the distance is always larger and larger and larger. So the dendrogram always goes up because of how the y-axis is defined. With centroids, sometimes they get closer together than the previous partitioning, and then the dendrogram goes down again, which is kind of weird. So, and these are just some alternative visualizations for dendrograms, which you can also use if you don't want to like use this for cutting, right? I mean, if the dendrogram itself is a result for you, if the dendrogram itself is what you want from the clustering, then you can visualize it in different ways like this. I like this one, for example. I think it's quite interesting. And this one is a bit weird, but it's also possible. Depends on what you want to do. So yeah, guys, there are some, let me just check whether I'm close. Yeah. So some other important considerations are what distance measure to use. The Euclidean distance is the most common, and you use the distance here in order to compute, like, well, the main thing about the clustering algorithm, which is which clusters you should merge at every step, right? And that is defined by the pair that has the lowest distance between each other. And even though Euclidean distance is the most common, so you just take the vectors, compute the distance between them, and then that's it. You can also just use some arbitrary distance measure with arbitrary points, right? You could have a network and you could define the distance as the shortest path between 2 points, and then you could cluster that. Why not? That would work perfectly fine. If you don't need centroids, if you're not using like centroid linkage, for example, then if you do, then you would have to have some other definition of what a centroid is, because then you cannot compute a centroid anymore. But you could do single linkage or complete linkage, and that would work perfectly fine, because after you've computed the distances between every pairs of points, then that's all you need. You don't need the points anymore. All you need is just their distances, okay? So just keep that in mind, because that's also useful for your assignments and the way that you're gonna write the stuff, your code. That is important. Oh yeah, I haven't talked about the optimization yet. So should you normalize the features? Normalizing the features removes different effects from different units. That's interesting. Oh yeah, and actually, just a very quick, I forgot, sorry, that this was related to the distance measure that I was talking about. This is something interesting about how different distance measures will affect your clustering in different ways. For example, think about the yellow observation here that goes up and down, right? So think about this as one point, let's say, or one observation. It goes up and down, up and down, up and down. Then you have the green observation, which also goes up and down in more or less the same way. So whenever one goes up, the other goes up, and then whenever one goes down, the other goes down. But they are in different scales, right? One is like between 0 and 5, and the other one is between 5 and 15. Although they are very similar to each other in terms of behavior, they are distanced by the actual values of the observations. While the pink one down here has no relationship whatsoever with the yellow one, because it's kind of random, right? It doesn't really have a pattern. But due to the fact that it sits more or less in the same range between 0 and 5, if you compute the Euclidean distance here, these two guys here, the yellow and the pink, will be much closer to each other in terms of Euclidean distance than the yellow will be to the green. So in this case, what you need is to define a new distance measure that takes into account what you want it to take into account. So I want to take into account the fact that they go up and down together somehow, even though they are far away from each other in terms of actual values. So I want a distance measure that reflects like behavior of the points. Then if you define these new distance measure, then you can just plug it in the algorithm and then cluster in a completely different way. So that's why it's very important to remember that distance measures, like the Euclidean distance measure, is not the final one. Okay, it could be other examples also. Should you normalize the features? Maybe or maybe not. Normalizing removes some effects. Like for example, this is like a difference between people who have go to a supermarket and buy like socks and computers, right? So obviously, if you go to a supermarket and you buy socks, like you may buy a lot of socks, right? You may buy like eight pairs of socks, or 10 pairs of socks, or 4 pairs of socks, but not computers, right? If you go to a supermarket to buy a computer, or to a store or anything, then usually you just buy one computer, right? You don't buy a lot of computers. So this makes it so that, for example, these two variables, they are very far away from each other in terms of their values, right? And if you normalize them, for example, you normalize them by between 0 and 1, or between, or using the standard deviation anyway, doesn't matter too much, then in a way what you're doing is you're equalizing the effects of the scale of the variables, right? So you don't care too much anymore about the actual scale, because the scale of one computer against 0 computers is not the same as the scale between 0 socks and 10 socks. You don't expect there to be a person who goes to a store and buys 10 computers, right? So it's important to kind of like equalize for that in a way, because for example, on the other hand here, if you use price as a variable, then obviously socks will be all the way down here because they cost like, I don't know, $1 or $5, while a computer costs like $2,000, right? So again, this is not good. The important thing here is that you have to remember that whenever you have different variables that are completely different to each other in terms of scale, then usually you should normalize them so that you don't really care about the effect, those effects anymore. And that's very important. That's kind of like part of the data pre-processing step. And finally, about the optimization, the original complexity is cube, so O(n) to the third power. So cubic, actually not cube, but can be made into a n. I don't know how to say that in English, but n to the second, n squared log n. Let's say, I guess, n squared log n, with the use of a priority queue. What is a priority queue? A priority queue is a data structure where everything you put into it is always ordered. So if you take all the pairwise distances between all points, and then you put them into a priority queue such that they are ordered, then all you have to do in order to take the smallest one is just to take the top of the queue, because that's the one with the highest priority, so to speak, because that's the one you want. It has the smallest distance. However, when you merge the clusters, you have to update the priority queue also, and that's not super simple, but it's possible. Just you can take a look at the course literature if you're interested in that, and also this the source of this this figure here, where they explain what a priority queue is and how to implement it, if you're curious. Yeah, for sure. I forgot about that. You for sure don't have to check all the combinations. So Christian said, since the distance is symmetric, we don't have to check all the combinations, but half, right? Yes, that is absolutely true. Actually, not even half, but less than half, because you also don't consider the diagonal, like you don't compute distances from points to themselves. So it's actually n squared minus n divided by 2. Which is still like the complexity is still n squared. Okay, so it's not like, okay, of course it helps, but as the data set gets bigger and bigger and bigger, the complexity is still n squared. So it kind of like grows very fast anyway. But that's absolutely true for every, that's true for every algorithm that uses pairwise distances, be it them clustering or dimensionality reduction or any other that uses pairwise distances. You almost never have to compute the whole thing, but that's only for Euclidean distances. Okay, for example, if you take shortest paths in a directed graph, then they are not symmetric, and then you would have to compute the whole thing. But those are special cases. So in general, you can assume that. And also, you do not need to always compute all clusters. You can use some criteria to stop the process, like you can see in the course literature, where you compute some kind of error and then you can stop if you think that the error has gone up too much or something. And in all Euclidean spaces, you can use this thing called clustroids or midoids instead of centroids, but I won't go into that because those are cornered cases again. And again, you can read about them in the literature if you want, but that's not required. Theoretically, we would have a break now. If that's okay, I will not have a break because we had to spend 15 minutes talking about the assignments in the beginning. So if I have a break now, then I will not be able to get into the important stuff. So please forgive me if we don't have a break right now. Yeah, so some things here that we have to consider so far is that clustering techniques usually force every instance to be assigned a cluster. So outliers which are not clearly part of any cluster may distort the results. So basically every point must be in a cluster, and sometimes some points are just noise, and you don't want them to be in any cluster because they don't help at all. Actually, they get in the way of a good clustering. And clusters are usually not very robust because different subsets of the same data set will yield different clusters. So for example, if you take a data set and you break it down into 2 different sub data sets and then you cluster, they might give you completely different results, which they shouldn't if you consider that the clusters are robust and they represent an actual pattern that comes from the underlying phenomenon that you are representing with your data set. So they shouldn't, but they usually do. And that's why now we're going to introduce this thing called db-scan, which is density-based spatial clustering of applications with noise. So that's a nice acronym, db-scan, but that's quite a long, complicated name. And this is not really a new technique that came out, I think, like 96. But it's still heavily used. It has been improved in many ways. The original one is kind of not used anymore, but there are improvements of it that are still used. But knowing the base means you know like 90% of what you need to know in order to understand the improvements. So we're going to stick with the classic one. And so density-based clustering means that points that are close together will belong to the same cluster, and isolated points will be left out of the clustering. So that's why it's density-based, because if a certain point is an outlier and it is not in an area with enough density of points, then we just say, okay, that's noise, and we don't care about that. We just consider that doesn't matter. It's for the specific problem of extracting clusters, right? And one of important definition here is an epsilon neighborhood of an element, which is basically just all elements that are closer to x. Well, the distance to x is smaller than epsilon. Epsilon is a parameter, okay? So you define there like 1.5 or whatever, depends on the scale of your data. But you just define there something like 0.2, and then that means that every point in the radius of, or inside the radius of 0.2 is considered to be in the epsilon neighborhood of a certain point x. And all points will have their epsilon neighborhood, and you see that sometimes they share neighborhood. Like for example, Q and P here, they have one point in the middle here where they have this, they are shared in these two neighborhoods. But then there's a point over here who is in P's epsilon neighborhood, but not in Q's epsilon neighborhood, right? So this is important for doing the density search. And if you've done kernel stuff, kernel density stuff, you know that it's more or less the same thing. So simplified algorithm, find the epsilon neighborhood of every element of the data set. Basically what we see on the right hand side here. And going back to Christian's question, yeah, at this point, in order to find the epsilon neighborhood, if you're doing this in a very, very simple way, then yeah, you have to check all pairs of points again. Because for every point, you will have to check all other points to see if they are indeed inside the epsilon neighborhood of every element or not. However, the most common optimization here is to use something called an R star 3, which unfortunately I cannot go into details on that, but that's like an indexing thing where you do a specific thing in order to generate this tree, and then every point goes into this tree, and then from this tree you can retrieve the neighborhoods of points in a much faster way. It takes a while to build the tree, right? So it takes actually quite a while to, I mean, it's not super fast to actually build the tree. And that's why usually this is done in like databases or something like that. But it takes a while to build the tree. But after you build it, you have a data structure that allows you to recover the neighborhoods of points very easily, very fast. So one thing you can do in order to optimize this is to build this actual R star tree. Okay, R star, you know, like an asterisk. You can search for it later. But anyway, recover the epsilon neighborhood of every element. If you have to compute, if you have to check all elements against all other elements, then so be it. Then you assign all elements that share a neighborhood to the same cluster. Again, this is a simplified algorithm, right? You might ask yourself, like, how can I do that? You will see that in the actual paper that I linked to you. So you just start from a point, a certain point, then look at its neighbors, and then just put them into the same cluster as this guy, and then do that recursively. So after you do that, you jump to the next points, and you do the same thing, and you jump again and do the same thing, and so on. Okay. But basically, yeah, assign all elements that share an epsilon neighborhood to the same cluster. And as you can see here, these guys share a neighborhood. This guy is alone because it doesn't. These guys share a neighborhood, and this guy share a neighborhood. So we end up with 4 different clusters so far, right? But that's not all. Elements who have less than min, let's say, points in their neighborhood are considered noise. So this guy here, for example, if you consider its own neighborhood, it has just, so I'm considering min here equals 2. So this guy only has 1 point in its neighborhood, doesn't count. This guy has no points in its neighborhood, doesn't count. This guy also doesn't count. These 2 guys, they only have each other in their neighborhood, so they don't count. And this guy also, I guess, considering here, it's touching this one, but not really this one. So it's just noise. As so far. Because then we have a next step where I have a corrupted slide. What happened here, guys? I have no idea. So I have a it's one slide inside the other slide. It's a recursive slide. Oh my God. Oh my God. Unexpected problem. Let's fix it very quickly if we can. Wow. I have no idea what happened. Probably I copy pasted something and didn't even notice it. Let's see. Yeah. All right. I guess that's it. So pretend that nothing happened. And so we were up to this point where elements who have less than minimum points in their neighborhood are considered noise. But there's a final step where it is that unless they are in the neighborhood of a core element. And a core element, I forgot to put that here, but a core element was an element that was not considered noise in the previous step, right? So first you go and you check all those like noise candidates and you mark them as noise candidates. And then you go to the other points and you check again, like the core elements that were left. Are they reaching for a noise element, a candidate noise element? If the core points are reaching for a noise element in their neighborhood, then again, they're reassigned to the cluster, okay? But these guys, like this guys here and this guys here, they were not reached for by any other core element, so they remain noise. And that's it. That's the final result. And then you have these core elements, which are basically just, yeah, absolutely parts of the cluster. You have these border elements, so to speak, which are the elements that were considered as candidate noise, but then later they were turned into cluster points because they were reached by the core elements. And then you have the actual noise, which is just noise. So you don't necessarily remove them from the data set, but you just mark them as noise and just leave them there. Please, Daniel, go for it.
Yeah, but is that also a recursive step? Because I imagine that once you treated some of the noise points,
yeah,
they will then become core points. And then maybe some ones of the first step, if you had sort of a chaining out, if you can see what I mean.
Yeah, I see what you mean.
Then you would have to revise that step a
yeah.
number of steps to sort of get the whole chain, because they are attached, but the core points arrive at different points in time. If you
yeah, I understand what you mean. Do you mean, just confirm to me, you mean that border points would become core points and they themselves would reach out for more border points, right?
Correct. And there is actually no way of knowing how many times we need to iterate that step.
Yeah.
Do we iterate it until there are no more core points made, or just one go?
No, border points are border points. So that's why you don't call them core points, because they're just border points. So as you do this just once. Now, I don't want to be like that guy who says I know everything, because it is a good question. So there is a small possibility that they may say something about this in the paper that I don't remember, but I will I give you like 90% certainty that that border points are just border points and they don't reach for new border points after that. Okay. So let's assume that I'm pretty sure that that's the case. Of course, maybe you read the paper and then you say, no, they're talking about this in this section. Then I will gladly record a errata if that's the case. But I would say I'm almost sure that no, because that would be very dangerous. That will just go on forever, right? And I don't think that's the some new versions of DBScan don't even consider border points anymore, actually. I think the most used ones, like optics and the HDBScan, they don't even consider points as border anymore. There's just like core or noise, and that's it. So I'm almost sure that no. And these are some examples. This is definitely something that you cannot do with k-means for sure, right? K-means would never be able to separate like these two things that are intertwined with each other here, because k-means only creates convex clusters, right? Never concave clusters, let's say, or non-convex clusters like these ones. It's impossible to get this with k-means. You might have a good result with hierarchical clustering, because hierarchical clustering is also very like unconstrained, so to speak. But the problem with hierarchical clustering is that as soon as you connect one cluster to the other, and that just never disconnects again. Then that goes on and never, and from that point on, it's always going to be connected. While with DBScan is a little bit more flexible. It's highly non-linear, right? It's like a highly, let's say, complicated in a way optimization process from a mathematical point of view. But it does get you very good results. And maybe one of the more interesting things is the noise, right? Because it really allows you to just ignore some points like in this case, for example, there are all these points that are just lying around the data set. They don't mean much, so they shouldn't actually mean much. And this is just an example here of the core points, the border points, which are the blue ones, which are closer to the core, and then the noise that's actually just noise. And by looking at it, I'm almost sure that for sure there's no recursive thing here, because or else the border points would definitely reach for some noise, some new noise points here, like here, for example, or in other places like this. So I'm pretty sure that no, we don't do that recursively. Anyway, this is a very interesting result, because this is, you can see the flexibility of dbScan, which is really cool. And then we have a simulation for dbScan. Let me just check what else we have here. Yeah, so I will actually go for this simulation because I think dbScan is very important for us. So this is the website. Oh, you don't see the website. Sorry. Let me change to the desktop. Yeah, you see the website now, right? You do, right? Oh, sorry. I have a question from UM189020, whoever that is.
Sorry, it's me. I don't know why with this account.
Yeah.
Lisa.
Oh, okay.
I just wanted to ask, how do we decide on the number of connection we need to have for it not to be noise? If we have a really large network, you can't really even visualize it. How do you decide?
Well, the algorithm has two parameters, right? Let me just go back to it very quickly. So, well, in this case, we're not talking about networks yet. These are just multidimensional points with distances between them. But of course, you could consider, if you could just abstract away the network and just compute distances between nodes, and then you could still use the algorithm. But there are basically two parameters here, which is the epsilon of the epsilon neighborhood and the minimum of points that you're considering. But so hyperparameters are always a problem, right? It's very hard to say for sure what you do in order to define the hyperparameters, in this case the epsilon and the minimum of points. But I have this slide here. I can just skip to it and then I can go back to the other one later. So when it comes to the hyperparameters, again, you have two, which is epsilon, the radius of the neighborhoods. I guess in a network that makes very little sense to think of a radius, unfortunately. I don't know how you would, I mean, you can still do that, but I guess it would be a little bit harder. And then you have the minimum number of neighbors that you can consider in order to you are noise or not. So how to pick them? Complicated. There is a discussion about this in the course literature that you can take a look. I think it's a little bit complicated discussion, so I didn't include this as like a required reading, but it's optional and you can take a look at the course literature where they discuss this. But I would say that it's either trial and error, unfortunately, or it's the elbow method again. So for example, you can fixate a certain minimum of points, like 10, and then you compute the distance from every point to their 10th neighbor, for example. And the elbow shows a possible value for epsilon, right? So let's say the distance. So if you fixated this, and then you go to your data set, compute the distance of every point to the 10th neighbor, for example, and then you will have some, at some point it will go up like this, and then you take the elbow, because that will mean like most points are, below, most points have their 10th neighbor below this certain radius that I have defined. And then you can use that as a parameter, because then the rest, those who are farther away from that value, from the 10th neighbor, they could be like outliers. You can consider, well, not outliers, but at least candidates for outliers. So that would be one way to kind of define what the epsilon is. To define the minimum, it's very hard because this comes, if you consider other algorithms where you have to define the k, or as in like k neighbors, it's always the same, right? Sorry. Yeah.
I understand. Okay, thank
Yeah,
you.
okay, that's okay. All right. So yeah, try on error, unfortunately. And it's the same thing for every algorithm that asks for a k number of neighbors, which is unfortunately very common, and we don't really have a final answer for that. Now let me see here. Yeah, so this is the simulation. We're almost at the end of our time. I will go through this slightly quickly, and then we can discuss the rest of the whatever it is that we need to do. So let's just take some kind of data set here, like a Gaussian mixture, which is probably the easiest thing, right? So a Gaussian mixture is just basically a bunch of normally distributed clusters separated from each other. And that's what we have here. I have one group here, and one group here. So forget about these circles for now. And now I'm going to press go. There are some parameters here, like the epsilon, the minimum of points here, right? So I can change them if I want. And the circles here are just kind of like representations of more or less what it means. It doesn't matter too much. And also the minimum of points, you see, like it shows where, because I'm at 4 here, so it's only showing circles with 4. But it doesn't matter because the algorithm works in another way. So this is a representation of the algorithm working, right? So you can see that they started from a random point somewhere. They started so that random point reached for other points and made those other points part of the cluster. And then recursively, the other points also reached for other points and also added them to the cluster and so on. Until at some point, in this case here, at some point there were no more points because the points there couldn't reach anyone anymore. And then in that case, you jump to the next random point that has not been assigned a cluster yet. And then you start again and start reaching. And then you can see that some points were left out as noise because they couldn't reach anyone and no one could reach them either. So then they were considered as noise. And I'm gonna go back and try another. Yeah, so I'm gonna try another one, like the smiley face, for example, which is not something that, for example, you can cluster with k-means. Actually, this guy has another. Yeah, he has another k-means simulation in which you can use to compare, because if you try to use k-means with this smiley face, you will see that it looks completely horrible. So, but with k-means, with dbScan, it takes a while. Unfortunately, it's a bit slow, but you will see that it kind of makes sense. And if it doesn't, that's because the parameters are not set correctly. But as you can see here, what happens is that the points are reaching out. I don't know why there are 2 different sources here. Maybe it's running in parallel, I guess. But you can see this, these 2 points, it's not running in parallel actually. I don't know why it started 2 different directions, but the points are just reaching for their neighbors. And at some point it's over. It's like, yeah, okay, I have no more neighbors. So jump to the next random point. The next random point happens to be in the mouth. So it's, again, going for them, and then again, and then again. And now we have 1, 2, 3, 4 clusters, which is nice. Looks a little bit creepy, but it's nice. And it's definitely something that you could not do with k-means. Maybe with hierarchical means, hierarchical clustering, but it's also not guaranteed. So yeah, dbScan, guys. And let me also now go back to this. Yeah, so I talked a little bit about the elbow here. So it's one way to find the epsilon. And finally, the strengths of dbScan are that it's robust to noise, obviously, because that's one of like the definitions, the ideas of the clustering algorithm. Finds clusters of different shapes and sizes, which is really interesting. Especially when you're talking about multidimensional spaces. If you have these crazy manifolds that twist in high dimensional spaces, then traditional clustering algorithms will have a hard time with them. And dbScan can find clusters of different shapes because the shape actually doesn't matter, right? If you think about the algorithm, it doesn't really matter. Yeah. Oh yeah, Christian said, yeah, I think it might do them in the order of insertion. That could explain why it went both right and left. Yeah, you're right. I mean, because for some reason during the assignment of the, let's say, the children, there's one children went one way and the other went the other way, and I guess it doesn't matter because they were not running in parallel, so they're just like going back and forth. You're absolutely right. It's just a random effect, I guess. The weaknesses of the DB scan is its sensitivity to parameters. So you can see an example here on the right-hand side. Different parameters for the epsilon, like from 9.92 to 9.75, basically kind of like changed completely the results, right? You'll still see, like, because of the density, you still see these 3 clusters over here. But in this case, they were just one big cluster. Even though they are not one big cluster, and at the same time you lost the information from the other clusters which are less dense, right? So epsilon here really just changed everything, and it cannot adapt to varying densities. Again, that's also what happened over here, because you have these clusters that are kind of like intertwined with each other, although the densities of these 3 guys here, they are much more dense than the big one. So it couldn't really adapt to that, which is interesting and unfortunate, but you know, no algorithm is perfect. So yeah, now before you go, guys, if you can just hang on for 5 more minutes. Oh, sorry, Artemis, you want to ask a question, please? I didn't see it. Sorry.
No, it's actually I just want to know that so in some case the focus is not really on the borders, it's just more on cores and noises. Yes, because as you show in the websites, they didn't show any borders. It was just noise and.
Yeah, that's a good question. In a way, you don't really differentiate between border and core. In terms of whether they are cluster points or noise points, period, right? I think the only reason why you have this distinction between core and border is because of what Daniel asked, like you don't want border points to keep reaching for more border points and so on and so forth, because or else that will go on forever, I guess. So I think the distinction here is just because the core points reach for the border, but the border is like the last step, and then it stops there. But both are basically just cluster points, so that doesn't matter. Okay. Yeah. So now, guys, here's the thing. As you will see when you read the assignments, and we can discuss this tomorrow. DB scan is your weekly assignment. Okay. Like I said, classic DB scan, original DB scan. Don't worry about optimizations. Don't worry about any kind of R star tree or whatever. I mean, if you want to do it, go for it. It could be a learning experience, but it's not required. So just go on and just compute every pairwise distance, because the data points, the data sets that I will test on, they're not huge. They're just reasonably small. It would be better if you're using Python. It would be better if you use NumPy, and if you try to optimize that as much as you can, please, because pure Python is ridiculously slow and should be a problem, actually, if you want to compute pairwise distances. So go for NumPy and try to make it at least slightly vectorized, you know, because then it becomes a bit faster. But again, the data sets that we will test are rather small, because the important thing here is that you understand how the algorithm works and that you can reproduce it. Yeah, so that's it, and we're gonna come back to this tomorrow. There is an extra set of slides. I have an extra set of slides that I will record and send them to you later. They are also important. There are 2 things that were left behind. One is cluster validation, which is about external validation of the clusters in a way that you can compare different clustering techniques with one same quality measure, because you know every clustering technique has its own optimization target. So you cannot compare them if you use their own like optimization targets, right? So you have to compare them using some external validation metrics. That there's a set of slides on that I will send to you. And there's also a set of slides on one state-of-the-art example of clustering and how it's used in scientific research, which I also want to show it to you. So I will record that and post it, and then you can watch it later. Should be like half an hour, 40 minutes total, both videos probably. Okay. And that's it, guys, for today. Thanks a lot for coming. Thanks a lot for all the questions. That's a good change from previous ones. Keep them coming, please, because I like them. Have a great weekend. Well, for those of you who don't come tomorrow, have a great weekend. We will talk next week again. For those of you who come tomorrow, you are very much welcome. Bye-bye.
Thank you.
Thank you.
Bye.
Bye.